And our first invited speaker is James Hayes. James is a principal scientist with Argo AI and an associate professor at Georgia Tech. His research interests span computer vision, robotics, and machine learning. And James has developed like a variety of data sets, but in particular, he worked on Argoverse, which is a large-scale data set for self-driving cars. Thanks for joining us today, James.
Thank you for having me. It's great to be here. Thank you for organizing this workshop. So yeah, I'm going to talk about the Argoverse workshop, Argoverse data set, or one particular slice of it that focuses on motion forecasting. And like Jennifer said, we've seen a lot of biological stuff so far. This is going to be motivated by self-driving. Let me just give an outline and then show examples of what I'm talking about. So we're going to define what this forecasting task is, how they've improved over the last few years when we've had this data set out, what the top methods are now, where they still fail, and what we can learn from the techniques used by these top methods. And then at the end, I'm going to advertise a couple of new things, a new Argoverse retrieval benchmark and a new Argoverse, basically. Let's define this forecasting task first of all. So side by side here, you'll see the same scenario, and you'll see two algorithms trying to forecast the future for it. So in the first Argoverse, the Argoverse right now, you see 2 seconds of trajectories. So this is a bird's eye view of a road with you've got HD maps underneath all of these different actors. And the focal agent is the one in orange here. I know the compression might make it hard to see. And you see 2 seconds of it, and then, didn't mean to advance. And then you need to predict the next 3 seconds of the future. And once that 2-second observation stops, you see now that these algorithms are rolling out 3 seconds of future just for that particular focal agent. And let me go back to this. Sorry. Video playback. I apologize. Just pause near the end here. And so this vehicle went forward and took an unanticipated right turn. It was approaching this intersection, but you couldn't really have known it was going to turn right, although you might have had a hint because of the road map that's available with this data set. And the algorithm on the left didn't do a great job with that. You can see that it enrolled 6 possible future trajectories in green, but it assigned 0 probability to the one that had a right turn. That's what that number is there. This algorithm did a little better. It said, okay, a right turn is possible and 0.15 probability, which is not bad. Both algorithms knew that the car wasn't going to go through the intersection. I think it was already slowing down, so they could tell that. And you see all these other dots for other actors in the scene, which might inform the motion of this one that we're asking about. And this task is important for self-driving because humans are effortlessly doing this task all the time, predicting how the other cars, pedestrians, and bikes around them are going to move. And so it's important for the AVs to do that so they can drive safely, but I think even more than safely, just naturally and without constant interruptions. So that's what the algorithm output looks like. Here's another visualization of that. You get to observe 2 seconds, you forecast 3 seconds. You can make multiple guesses. We usually use a setting with 6 guesses. It's just showing 2 here. So how do we quantitatively evaluate whether an algorithm is doing a better job than another algorithm? Well, we focus on endpoint error. So here's one trajectory, and here's the endpoint of that trajectory. And in red is the ground truth. So this one's pretty good, endpoint error. That's distance 1 here. And there's a probability assigned to each of these. And the probabilities will sum to 1. And so in the past, we've just evaluated these by what we call minimum final endpoint error, final displacement error, D1 here. And the lower, the better, of course. We've also looked at miss rate, which is just a hard thresholding on that, basically saying if your miss rate's less than 2 meters, you got it right. If it's more than 2 meters, you got it wrong. And in the most recent iteration of the competitions, we've used this Breyer min FDE, where we actually look at the probabilities that you're giving us for the first time and say that your score and lower is better is based on your distance, but also how high this probability was. If you gave that one perfect probability, then you don't have any additional penalty. If you didn't, you've got some small additional penalty to your distance, basically. And yeah, if your probabilities were perfect, then this converges to just min FDE. And we've used these 3 different sets of quantitative evaluations for 3 different sets of competitions over 3 years. We're just finishing up one today, actually, later this afternoon at the workshop on autonomous driving. So I have a new, fresh set of algorithms to talk about. And we've seen a lot of competition submissions, 229 teams over the course of the 2 years that this has been public, 70 teams in this most recent iteration. And a cool thing to see is that even though we've been switching the sorting metric for the leaderboard. And right now it's sorted by this Breyer min FDE, and these are the top 5 methods. The top methods are doing better according to all of the metrics, which is definitely good to see, and dramatically better than the baselines we started with years ago. Here's just a plot showing progression of or reduction in error over time by the top methods. So the 2019 contest winners, the 2020 winners, and 2021. And this is if we look at only one of these metrics, min FDE, the endpoint error. And for example, in 2020, endpoint error was not the metric we were sorting the leaderboard by, but still the top methods that came in during that competition did better than the methods in 2019. This is a significant reduction in error. I mean, if you look at the absolute error here, it's getting pretty low. And then again, this year, again, another substantial reduction in endpoint error. And the same thing for miss rate, even though that's not how we sort the leaderboard now, these algorithms are doing way better. In particular, this method, which I will highlight later, Team Stefano, one of our honorable mentions this year, just amazingly better than previous algorithms. So it's cool to see all this progress. So what do these algorithms look like at a high level? We don't have time to go into details. This is what the top methods in 2020 looked like. They all have some way to encode trajectories, not just of the agent usually that we're asking about. We're asking about the future for one particular car, but also for other agents in the scene. You might want to encode their trajectories somehow. Usually things like 1D LSTMs or 1D convolutions. You need to encode the map as well. I mean, you could have a method that's map blind, but it wouldn't work as well because the map really tells you a lot. The cars tend to follow the lanes. Not always, though. There's also map violating behavior. You need some way to handle social interaction to understand that one trajectory for the agent and one trajectory for another object in the scene are probably not going to hit each other. So you should understand that social interaction when you're trying to predict the future. And then all of these things, somehow get munged together, and then you have some decoder that will actually unroll the future. And all of these things can be different. Some of them are vectorized, so to speak, and some of them are rasterized. That is, the map representation, including one of the honorable mentions this year, might be an actual human interpretable image that goes into a deep convolutional network. And these methods are actually competitive, even though it seems like sort of a weird way to do it, to just render this abstract scene and then have a CNN decide on it, but it can work quite well. And this bottom one from Uber, from Raquel, who I think is our next speaker, right, is actually, I think, deserves special notice. It was one of the top methods last year, but this year, 3 of the top 5 methods build on Lane Graph Convolutional Network, Lane GCN. So I'll just give an overview of what their architecture looks like, which seems to have inspired so many follow-ups that have improved upon it even further this year. Again, they have some method to encode the trajectories of actors, a 1D CNN in this case, through a feature pyramid network. And they have some way to encode the graph of the map itself that is under the scenario. So they're not using a rasterization-based approach. They're using a graph convolutional network to communicate across this graph. And then they have some mechanism for these things to talk to each other, basically. Actors can talk to other actors, lanes can talk to other lanes, and so on. And then at the end, you have some decoder that unrolls this into some number of future trajectories, 6 for most of the metrics we're using. And the first place team this year from QCraft, I'll just let them present on their own. They have a 2-minute video here. And if I shared my audio quickly through Zoom, you should hear this. Let me know if you don't. But I'll just let this play for 2 minutes.
Hello everyone, I'm Fang Da from QCraft, and we're here to briefly discuss our submission. Our main technical innovation is a new long-range graph attention mechanism for encoding lane graphs in the HD maps. This work is currently in submission for peer review, but we will try to outline the main idea here. The design is motivated by our observation that lanes in urban areas can form very complex arrangements from combinations of basic interaction types such as neighbors, successors, and predecessors. And in these arrangements, lanes would often interact with other lanes that are not directly connected to them. For example, in Argoverse, there are many scenarios where a car finishes a turn and enters a lane that's not connected through the turn. Here's another scenario where a car is about to finish a shallow merge. Here it could be interacting with traffic 2 lanes over to the left. Existing GNN structures such as graph convolution and graph attention would treat these non-local interactions as composition of local one-ring interactions. But these interactions are conceptually different, and such a composition doesn't really make sense. So we need more expressive power to capture the long-range interactions. This motivates us to develop a more flexible graph attention mechanism using the connectivity path between lanes. We find that encoding the HD map using this new graph attention gives us a significant boost across all metrics. Our overall prediction framework is built on top of Uber's lane GCN work. In addition to using the new graph attention we just talked about, we also changed the trajectory classification loss to a negative log likelihood loss on a Gaussian mixture model. And we built a model ensemble using k-means to aggregate the trajectory modes. We find that these two changes didn't make a whole lot of difference on ADE and FDE, but they improved the trajectory probability prediction, and so they improved the Brier scores a lot. That's all of our report today.
Okay. Didn't mean to exit totally out of that presentation. So yeah, they won first place in our competition.
Hello everyone, I'm Fang Da.
Stop playing. And I'll highlight another honorable mention team that did quite well and has a very different approach because their approach rasterizes both part of the input and the output. So here's visualizations of what this method is doing. So the output is this heat map that you're seeing visualized here, which is where the endpoint might be for the object in question, the agent. So it's the blue car in this visualization. And here you can see the actual trajectories with the probabilities associated with them. And let me just show the architecture of what they use here. So they render, again, this is a human interpretable image that goes into a standard convolutional network at sort of ImageNet-ish resolution. And that's how the network understands the map and the other agents around. It also has an encoding for the observed motion of the object in question, of the other objects. And these get encoded together through some social encoding, then everything gets encoded together before some decoding unrolls a heat map, or not the trajectory directly, but a heat map instead. And through that heat map, the different endpoints are sampled. And again, the ground truth position is just a single point in that heat map. This method did exceptionally well at miss rate, which meant it was exceptionally well at getting coverage of these possible endpoints, way better than any of the other methods. And this is how they actually select those endpoints. It's actually just a greedy algorithm. They're picking peaks in that heat map of where that object might end up, and then greedily selecting the most likely, 6 in this case for our competition. But it worked well, better than all the fancy, transformer-based methods or LSTM-based methods, at least for picking a good set of endpoints. So it's cool to see these different approaches. All right, so I'm going to now look at where these methods don't work so well, because we've seen the numbers have gotten so much better over the years. What is still difficult? Like this is what I showed at the beginning, these unanticipated turns where you don't know what the object is going to do unless you look at the map, and then you might have a guess, but of course it's still fundamentally ambiguous. And some algorithms do better than others. The algorithm on the left didn't have a great job assigning probability to the right turn. The algorithm on the right did a little better, having a reasonable probability that this unanticipated turn could happen. All right, another scenario where they have even more difficulty is when there's extreme velocity changes. So let me play this. I'll play it a couple of times. So we see the agent, you can tell by the length of that trail behind it that it was moving at a pretty high velocity. And then the ground truth in red, that's 3 seconds, the observed time is 2 seconds. The ground truth shows that it decelerated quite a bit. This shouldn't be a huge surprise because we also see there's all these other vehicles in front of it. So it had to have slowed down so it doesn't cause a collision. But not all of the methods seem to realize that and have it sort of barging through traffic and maintaining. So these are pretty high probabilities for high velocity trajectories into the future. This method on the right did a better job of realizing that it's probably going to slow down quite a bit. And we've analyzed several of these challenging scenarios. So different columns here show the errors on these different types of scenarios. So on the leftmost is the full test data. So just to sort of calibrate this, the test set as a whole is this difficult. And things like lane changes, not a whole lot more difficult. But things like extreme velocity changes that I just showed have 2 or 3 times as much error as the test set as a whole. And again, unanticipated turns, I showed one of those earlier, substantially higher error. And the highest error, these common failures are scenarios where the previous competition winners didn't do well, and we're still having trouble there. So a lot of these scenarios are just fundamentally ambiguous, like the observed history doesn't show any motion for the object and it's sitting in the middle of an intersection. So you really have no way to know where it's going to start going in the next 3 seconds. Also, just a sanity check is to look at the correlation between the predictions between the top 5 methods on our leaderboard right now. And I guess the takeaway I would take from this is that the correlations are actually not that high. We did a similar analysis for other competitions and showed more correlation. So I don't know what that means. It means maybe that there's more progress to be made from ensembling or something like that, or that there's pretty diverse approaches being used here, because these correlations are not really in the 0.8 or 0.9 range. The one with the least correlation to the others is the one that is this middle row, that is the rasterization-based approach for the map. Okay, now what can we learn from these top performing methods right now? It matters how you encode the map a lot. That you can't just ignore the map, and beyond that, methods that add sophistication into how they encode the map and its attributes show benefits from that. A lot of them build on latent GCN, but have new bells and whistles to make the map encoding better in some way. So lane GCN again does, I think, deserve a lot of credit for influencing what methods are doing right now. We've seen methods that ensemble different models, and that does help. That's true of almost any machine learning task. And the fact that this is showing up in the top methods maybe means that this data set is saturating in performance. I don't know. It makes me worry when I start saying ensembling being the way forward. But it's helping. Methods that predict an endpoint first and then a trajectory second seem to show benefits from that. So it's one thing to consider. Again, fancier map features do help. And I guess, unsurprisingly, if you can train your model to directly optimize the leaderboard metrics, then that is helpful. For example, the Stefano method directly optimized miss rate and therefore perform much better than the others on that metric. Okay, that's the end of the overview of what top methods are doing now for motion forecasting in autonomous vehicles. I'll just briefly advertise a couple of things. One is a new retrieval benchmark that the forecasting team at Argoverse is releasing. The motivation here is that we have all of these scenarios, these track-like scenarios, not just in autonomous vehicles, but other domains. And it's just a fundamental task to be able to say, well, I have one scenario, find me similar scenarios. But it's not clear how to evaluate that, and there doesn't seem to be a good benchmark for that right now. So we're introducing the first one soon. And for example, you might have a query trajectory, as we see on the left, that this vehicle has turned left and then changed lanes and queued behind another object. And here's 2 possible relevant retrievals for that. Of course, it's really hard to define what's relevant. So in this case, relevance is defined in terms of intent, where there's these intents or attributes of the scenario where one intent might be turn and then change lanes. That's what this middle one is showing. And another intent might be queue behind a leading vehicle. So it's hard to know what the intent of the user was when they said, okay, find me similar trajectories to this query one on the left from the laser pointer. But if their intent was turn and then change lanes, then this is a good retrieval. And if their intent was queue behind the leading vehicle, then this is a good retrieval. And these intents have been manually annotated by experts for thousands of scenarios so that we can benchmark different retrieval methods. And here's just a number overload of what current results look like. I think the thing to take away is that these numbers are not good. One would be perfect retrieval results. So if I ask you for the 10 nearest neighbors in a data set, then this is the proportion of them that are relevant according to different distance metrics or encodings. And they all have a long way to improve. And it gets worse the more retrieval results you ask for, unsurprisingly. So yeah, look for this data set to come out soon. And then the last thing I'll advertise, and this is actually the first time we're teasing this publicly, is that we released the first Argoverse 2 years ago at CVPR 2019, and we are going to be releasing a follow-up data set, which improves on Argoverse 1.1, shown here in a lot of ways, but for this, I'll just focus on how it improves the forecasting data set. So the forecasting data set, again, we've seen a lot of people using it, which is awesome, but it has some limitations. It has a lot of actors, but very little information about each actor, really just a centroid. The Argoverse 1 dataset does not identify the object category of an object in a scenario. So it could be a bicycle or a pedestrian or a vehicle. They're mostly vehicles. The time horizon's a little short. We've seen a lot of cool forecasting work that's looking at longer time horizons, and we want to support that. And things like traffic lights are not in the data set. So we're trying to address all of those things and also add a more geographic diversity. We'll span 6 cities now instead of 2, to add more diverse taxonomy. For example, the Waymo motion forecasting data set is excellent, but it only has 3 categories of objects, and we're going to have 10 plus categories of objects. Also underlying all of these scenarios will be improved HD maps that are richer than what's in the current Argoverse. Let me just show a visualization of what a scenario might look like in Argoverse 2. Again, we now know that these are cars. We didn't before. And we have a rough spatial extent because we know that they're cars. We now have HD maps under them that actually have full lane geometry, which wasn't the case in Argoverse 1.1. We only had center lines, and you could sort of inflate the lanes by assuming the lanes are constant width, and that mostly works. But now we have the full lane geometry available, which can make for better forecasts. Let me just show another scenario really quick, where we have now a bicycle is the object that you're trying to forecast the future for, and it's weaving through traffic and cutting in front of a vehicle here before turning down another lane. And we see the lane geometry here is, these lanes are very, very wide and unusually shaped. Argoverse 1 wouldn't have encoded that. Argoverse 1 wouldn't have encoded where crosswalks are. They're not visualized right here. So we are looking forward to releasing this much richer data set in the near future. Please keep an eye out for that. All right, and that's it for me. Again, the HD maps will be richer underneath all of this. Thank you. Yeah, thank you again for the invitation to this workshop.
Yeah, thanks a lot, James. We now have a question and answer section for, I think, 5 minutes-ish. If anyone from the audience would just like to unmute or use the chat to ask a question. So I actually had a quick question about the metrics that you were using. So I know that many things are important for self-driving cars, like safety and comfort and things you mentioned earlier. How do you design metrics of success for these? Because some of these things seem a little bit difficult to quantify.
Yeah, I guess that's fair. Like the metrics that we have right now don't directly encode things like passenger comfort, which is maybe the endpoint that you're interested in. So yeah, I think there probably is a room for improvement. And I mean, the short answer is we don't know the answer to this, which is why we've switched the metrics for the leaderboard 3 times. And we think we're making progress, but I don't think we have the whole story yet about what the right way to evaluate these things is. And there's a lot of constants in there that, do those really make sense? Like 6 trajectories, that's sort of the magic number now for a lot of methods. But is that really how we want to limit things? Or do we even want to evaluate methods as making discrete trajectory forecasting, or do we just want them to have a huge probability distribution of here's the possible futures of this agent? Yeah, I don't pretend to know the right way to do all of these things.
I see, thanks.
Maybe I can ask a quick question. Thanks for the talk, James. In the first a session of this workshop on animal behaviors, there was I think a fairly lively debate on how does one construct a taxonomy of behaviors, or taxonomy of scenarios. Can you comment a bit about how that manifested in the design of Argoverse 2.0, or your broader thoughts on that?
Right. So for the, I guess we don't, for Argoverse 1 and 2, we don't have to commit to a taxonomy of scenarios. We tried to find interesting scenarios through various heuristics, making sure that the focal object is doing something interesting. It's not parked. It's not just going in a straight line and so on. But for that retrieval benchmark that I advertised, yeah, there are various intents, which is sort of a taxonomy of ways in which scenarios can be interesting, like lane changes and things like that. And I guess in that case, it was just expert designed to try and cover a space of interesting behaviors. But yeah, I don't.
Right. I guess I thought I heard you mention that Argoverse 2.0 has 10 plus categories of scenarios in the forecasting. What did you mean there?
The 10 plus there is the object categories, because Argoverse 1 actually, you didn't know the object categories for agents. Well, for the agent, you know it was a car. For everything else in the scene, you didn't know. Whereas now we'll actually tell you in the scenarios that this is a bicycle or a pedestrian or a school bus and so on.
Thanks. I actually have another quick follow-up. So like sometimes I know it can be hard for humans when we are driving to predict how other cars might behave. By building these large-scale data sets, I guess like do we have an expectation that these models might do better than what humans can do?
Oh, that's a good question. Boy, it would be fun to have a human baseline. How would we, yeah, how would you get that baseline? If I had to guess, I would say that the models now are quite good and probably better than humans in some ways, probably not as good as humans in the ways that really matter. I think humans are very good at figuring out what the salient objects are. You know, there's dozens of objects in a lot of these scenes. Most of their motion is actually irrelevant to you. But there's a few really critical ones, you know, the pedestrian on the sidewalk who's sort of eyeing the road, like, oh goodness, could this person step into the road in front of me? I think humans have a very great intuition about where to focus their limited attention. And again, humans, if their forecasts probably, if you tried to make them into metric forecasts and unroll them into the future and said how many meters wrong they are, you know, maybe they're not great, but I think humans are probably great at I don't know, having a qualitative feel for this bad thing might happen. Let me drive defensively to avoid it.
Yeah, thanks. Would be really cool to see a human benchmark, although I also don't know what that would look like.
Yeah, that would be, that's a cool idea. Thank you.
Yeah, thanks for joining us for the talk.